Let me introduce Christian Forssén as our next speaker. He's a professor in theoretical physics at Chalmers. He uses high-performance computing, Bayesian statistics, and machine learning to address basic science questions within theoretical nuclear and particle physics. His talk will be about learning from data in fundamental physics research. Thank you, Christian. Welcome.
Thank you very much. Thank you for that introduction. It's nice to be here. So let me dive right in. I want to talk to you today about learning from data in science and more specifically in fundamental physics research. And of course, I know that most of you attending this talk are machine learning practitioners. And my hope is that you will get some inspiration out of the ideas and the underlying philosophy of what I will talk to you about today. And if nothing else, I hope that you will be at least a little bit fascinated by the science examples that I'm going to show you. We live in strange and difficult times, and I know that all of us need some fascination and inspiration from time to time. So this poster that I show here, you could find in a school classroom. It illustrates the scientific method, and the details of each step here could be adapted to whatever scientific discipline you are in. And in fact, I would say that within machine learning, you could probably recognize this sequence of an analysis. In fundamental physics, the hypothesis that stands at the center of the scientific method is usually framed as a scientific theory. And this scientific theory would usually have to be expressed in terms of a model. And very often we have to solve this model on a computer. And I will come back to the issue of actually solving the computer model later on in this presentation. A good scientific hypothesis should give falsifiable predictions that we can compare to data. And the analysis step involves linking the model prediction to the experiments. Of course, we want our model to describe reality, and we want our experiments to measure reality, and therefore we would like to connect the two of them. And this is a very interesting step in the analysis that I would like to spend a minute on. So we all understand and accept the fact that an experiment is an attempt to measure reality, and this is done with a finite precision. So we all accept that there are experimental error bars that we should take into account. Surprisingly, it's less accepted that a model also comes with uncertainties. We probably know when we set up the model that we have to do various approximations and that our model is not an exact description of reality. Furthermore, when we implement this model on a computer, we might have to do approximations, so our solution will not be an exact solution. And both of these things, of course, leads to errors or uncertainties. And one of my main messages in this presentation is that it's key to include both experimental uncertainties and theoretical uncertainties when you do the data analysis. And after all, having reliable errors is really what helps you to determine to what extent a disagreement points maybe to new physics, so that you have to revise your hypothesis, or if it's sort of within what you can expect. So I want to give you two examples that come from my own research and that are from very different scales of what we study in fundamental physics. So let me start at the microscopic scale. So the question of how we relate the inner building blocks of matter, quarks, and the theory that describes how quarks interact with each other. It's called quantum chromodynamics. And how do we link that to atomic nuclei and their constituents, protons and neutrons? And this, in fact, is a very difficult problem. And within our research, we use a fascinating theoretical framework called effective field theory. And obviously, I will not go into this subject here. But one of the really important outcomes of this theoretical framework is that it gives us a model prediction with a precision that gets better and better at each order that we go to in this effective field theory expansion. It's highlighted in the figure down in your left-hand corner where the arrow bands show the uncertainty of our model prediction. And those kind of uncertainties will certainly carry forward to when we make predictions, and they do, and we need methods in order to carry these uncertainties with us. Just as an illustration here, I show a very recent work that we are doing where we are studying the most extreme isotope of oxygen that you can imagine. We all breathe oxygen. This is oxygen 16. And the question that we're trying to answer here, if it's possible to form an isotope of oxygen that contains 20 neutrons, so oxygen 28. And this is also being explored experimentally. The other example that I have comes from the other extreme of scales that the fundamental physics addresses. In this particular case, I'm showing you pictures or signals from gravitational wave observations. This is a fascinating discovery that was made a few years ago and also rendered a Nobel Prize. What you see here are gravitational wave signals coming out from two colliding massive objects, usually black holes. And the wave signal here is then being compared to predictions from the theory of general relativity. And that kind of theory, that kind of model prediction contains parameters such as what were the masses of these colliding objects. And you want to infer that knowledge from the data. So that's a so-called inference problem. I would also like to mention what particularly fascinates me, namely the discovery of colliding not only black holes but also neutron stars, which was done also very recently. And through the help of having not one or two but actually three observatories, you can actually, using trilateralization, figure out where on the sky these objects are, and then you can direct other instruments to measure on them. And there's a wealth of interesting information coming out of these measurements. And we hope to learn more about neutron stars, but also about the synthesis of heavy elements, etc. But all of that learning requires us to handle both theory and experiment and their uncertainties. So learning from data, as I said, is an inference process, and we use it in science, and it's being used in machine learning as well. In science, though, there are maybe a few important differences that I would like to highlight. So first of all, in science, in physics, the model is usually traceable to an underlying theory. So this means that our models are constrained. There are theoretical constraints. The theory maybe predicts other observables as well. So there are other constraints on our model as well. Another difference is that the parameters themselves are often interesting in themselves, such as the masses of the black holes that I just mentioned. Another possible difference is that scientists are data producers. We typically do experiments, and sometimes the design of the experiment is in the hand of the scientist. So we can control various experimental parameters and what kind of data we are collecting. Also, we at least try to understand the errors of our data quite a lot. Another possible difference is that when a scientist judges the quality of a model, there might be different criteria here. So one of the criteria that is important is the interpretability. How do we understand the model? Another one that I've been dwelling on are the error estimates that we can do with a model. And another one is how predictive is it? And maybe some of this philosophy can be adapted in the machine learning community. So inference is a key topic that I've mentioned here, and in short that means the act of going from data or information to another proposition, such as a hypothesis. And what we are typically dealing with in natural science is so-called inductive inference, in which the data, the premises, they have bearing on if the hypothesis is true or false, but they don't allow us to make a definite determination. Basically, we don't. Our picture of the world is not black or white; it's more gray. And how do we quantify the strength of such inductive inference? Well, we do that using statistics, and the key quantity here are probabilities. And here I should mention there are a couple of different schools of statistics, the frequentist school and the Bayesian school. And I will spend the rest of this presentation talking about the Bayesian view on probabilities, as I do think that it's superior in science. And I would actually encourage more use of the Bayesian philosophy also in machine learning. So obviously I cannot give you a course on Bayesian statistics here, but at least I want to show you Bayes' theorem here. This is a theorem that actually comes directly from axioms of probability theory, and it connects probabilities to each other. And to be specific, it connects conditional probabilities. So as an example, let's consider that we have a model that has parameters alpha. And this model describes some reality, and we have data from this reality. This is D in the equation here. And there might be other information that also constrains our model. So what we are after is what we call the posterior distribution. So these are probabilities of the parameters alpha given conditional on that we have observed the set of data. Now, in following Bayes' theorem, that posterior probability is given as a product. I'll focus on the nominator on the right-hand side of two objects. The prior describes our prior knowledge about the parameters before we saw the data itself. And the other factor is the likelihood. And I think in many machine learning methods, this is what you would call a cost function or a loss function or whatever. And typically what you're doing is you're trying to vary your parameters so that you maximize this likelihood. In following Bayesian philosophy, it's a little bit more involved. And we could say that Bayes' theory formally encapsulates and formalizes the process of learning from data. And there are a few different advantages. One of them is the prior that I mentioned. This helps us to avoid common problems such as overfitting that we usually see when we try to optimize parameters. It also forces us to explicitly state our prior assumptions when we do the analysis. This is something that is otherwise easy to hide under the rug, but here we are forced to explicitly state them. Another key advantage is that Bayes' theorem forces us to focus on probabilities. It's less interesting to look at point estimates. What is the optimal value of the parameters? No, we have to watch the entire probability distribution. This will expose correlations between parameters. It will help us to quantify uncertainties, etc. As I said, I cannot give you a course on Bayesian statistics, but I can advertise that there is such a course called Learning from Data, which I developed for part of the master's program in physics. So if you're a registered Chalmers student, you can take this course. And if not, there is a wealth of material that has been developed for this course, and it's available on a Git repository, so you would be free to explore that if you're interested. So in the final few minutes of this presentation, I want to give you a glimpse of a very specific or particular machine learning that we have developed ourselves to address a specific problem that we have in our approach. So I mentioned the computer models that need to be solved, and sometimes that can be a very challenging problem. It can take hours to solve this model on a supercomputer. And if you want to do these fancy statistical studies that I talked about, you want to be able to do that for various values of the parameters in your model. So you would have to solve the problem over and over again. And if that now takes a long time, you of course are hindered here. So what we try to do is to create an emulator. And the basic idea is the following. You solve the problem a few times, you gather data from that, and you devise an algorithm that can learn from this data and make predictions without actually having to solve the model itself. So to be even more specific, the problem that I'm talking about is the quantum many-body problem. After all, I'm studying an atomic nucleus. And this, in fact, is a great challenge in natural science. And there has been great developments in the past few years allowing us to study ab initio, larger and larger nuclear systems, but this is still a very challenging computational problem. And to just give you a glimpse of how challenging it is, we use a method called exact diagonalization, in which you can frame the many-body problem in terms of a huge matrix to which you want to find the at least the extreme, the lowest eigenvalue and the corresponding eigenvector. And the size of this matrix can be 10 billion. So you would have a matrix that is 10 billion times 10 billion, and you want to find the eigenvector of that. And we can do it, but it takes hours on very powerful computers. So that hinders these statistical studies. So the idea that came out, and I should mention this came step by step. In the beginning, people or scientists didn't really know what to use these ideas for, but in the end it was clear this is a fantastic emulator for the quantum many-body problem. The idea is the following. It traces back to complex analysis in math and the idea of analytic continuation, but using eigenvectors instead. And these eigenvectors that live in this huge dimensional space, but as we vary the parameters, they actually follow a rather smooth trajectory. So if we can solve the problem a few times, find a few of these eigenvectors, we can trace this trajectory, and at the end of the day, we end up having to solve a tiny eigenvalue problem rather than this 10 billion one. This allows us to compute nuclei at lightning speed. I borrowed this movie from a colleague, Andreas Ekström. It shows oxygen-16 being evaluated hundreds, thousands of times in the matter of a few seconds. Here I'm plotting the energy and the radius for various parameterization of the forces between the nucleons. And as I said, we do this now in fractions of a second rather than hours. So this will allow us to do some rather fascinating science. And here I try to connect the first few examples that I showed you, because we think that through this strong interaction, there is a connection between the tiny atomic nuclei, such as lead-208, and the properties of massive objects such as neutron stars. And there's a connection between these two. And now we have experiments that measure properties of neutron stars. We have experiments that measure properties of atomic nuclei. And through the theory and these statistical methods, we want to connect these two. So by that, I end saying that learning from data is key in physics, not only in machine learning. I also would like to mention at the end that the solid foundation in math and problem-solving skills, I think, are key qualifications for a data scientist. And finding new solutions usually start with having to pose the right question, and I think this is where research training is important. Thank you very much.
Thank you, Christian. I mean, it always feels strange that you don't feel the applause at the end. It's always like it's a little bit of a black hole here, walking onto the scene without the audience in front of us. So we have time for a couple of questions. And I want to start with the fact that I'm a little bit provoked by the fact that you make a difference between AI practitioners and scientific research. Because, I mean, not all machine learning engineers are trying to predict cats from pictures. I mean, we're a lot about, I mean, it's called data science for a reason, that we actually try to use the methods from science to be able to give the decision makers or the companies that we work for actually the scientifically correct answers. And that actually implies that we need to use these techniques like the uncertainty measures and explainability and everything like that. And there's a famous paper by Galit-Shmeli, I don't know if you heard of it, To Explain or To Predict, where actually she mentions this important difference in terms of understanding the model or just using it for prediction. I mean, it's a little bit of the same as the difference between engineers and researchers, for example. Do you just build the bridge because you want to have a bridge, or do you want to understand why you build the bridge, or how you should do it? So, I mean, we're a lot of scientists out there that are actually using these methods.
Yes, so, definitely. I was being a bit provoking in stating that there is this difference. I of course understand there's lots of science here. I really want to stress the importance of understanding the prediction and the quantifying the uncertainties.
Right. And I think that it's very interesting the way that people try to use these Bayesian techniques even for these larger models that we're seeing apply right now, because that's really computational difficulty. I mean, people have been using Bayesian techniques for a long time, and that was particularly easy with smaller models. But now we're really at the standpoint it's really hard to be able to do that practically.
Yeah, this is a fascinating subject, and I'd love to learn more about that.
So let me just take one question here from Martin coming in. Do you see a future in using machine learning in various problem-solving tasks in fundamental physics? Perhaps in particle physics, for example.
Well, it's not just the future, it is being done right now. So machine learning is being used in the analysis of data, for example, in particle physics. So there is a problem of detecting various particles from the signals they give in detectors. So I think machine learning tools are excellent for helping with that.
Yeah, it's actually the fact that CERN, they use the gradient boosting trees to be able to find the Higgs boson.
Yes, no, exactly. So, yes, it is fascinating.
Okay, cool. Thank you for that. I think that's all the questions we had time for. And for the rest of the questions, you will have to answer them by email or Slack or something like that afterwards.
Thank you.
Thank you. And here comes Anna with no, it's not Anna. I mean, or did you cut your hair?
Thank you very much.
Thank you, Jacob.